Hello students, this is Dr. Siva Nagaraju, Associate Professor from IARE. Today we are going to discuss about error control coding. In that error control coding, we will again discuss one type is black code. So first, what is error control coding? In previous sessions, we discussed about different types of digital communication techniques and how to generate and what the probability of errors, all are discussed. But now we are going to control the errors. Why? After transmission, the signal is corrupted by the noise. So due to the noise, the receiver getting the error signal. For example, the transmitter sends symbol 1, but the receiver receives as 0. That means it takes the decision in favor of symbol 0, then it reads as 0. But actually what is sent 1, but it reads as 0. So there is an error. So how to control this error? This error control coding is nothing but channel encoding and channel decoding. Whereas earlier we discussed source coding. Source coding. So different types of source coding techniques are there, like Huffman, Shannon, Fano. So these come under the category of source coding techniques. Now here we're going for the channel, but saying like that as error control coding. Okay. So now coming to the topic. So this error control course coming to the course outcome as 6, and this topic is covered in module 5. So what the course outcome 6 says: build the black codes for error detection and error correction in noisy environment. So this module, this is the second part of this module 5, which covers with the black codes. Why? Here the cycle codes are there in this module, but the cycle codes come under the subclass of black codes. So that's why CO6, the course outcome 6, is dealing with the black codes only. So we are going to build the black codes for error detection and error correction in noisy environment. Okay. So first we'll go for the error control coding. So error control coding is the coding procedure done to control the occurrence of errors. Why? Due to this errors, we're having number of mistakes we're going to do. So we're going to control these errors. That procedure can be called as error control coding. So these techniques helps in error detection and error correction. So this error control coding is dealing with two types. One is error detection. First we go to detect the error in which bit sequence this error will generate, and error correction. Why? Here the sequence is just like 1100 like this, 110 1101. For example, this is sequence. In this sequence, binary sequence, first you could detect at what position this error is getting. For example, here you can treat it as this place. So in this place, we are first detect the error. That means in this position the error is takes. Means here it may be 1, but it has 0. So that is error detection, and after we are going to correct that error, that is error correction. So extra bits are added to the data at the transmitter to permit error detection or correction at the receiver. So here we are going to add in the redundancy. That is, we are adding the extra bits. Whereas in source coding, we are going to remove the redundancy. Why? At that point, I require the data rate is going to high and requires less transmission bandwidth. So that's why I'm going to reduce the redundancy for efficient utilization of the spectrum. Okay. But here, my aim is to control the errors by adding the redundancy. Redundancy means not essential bits. So these bits are not essential, but it is helpful to find the error and correct that error. Okay. So these bits, extra bits, are also called as parity bits. Okay. Now, the positions of the error control coding and decoding are shown in the transmission model. So, the next slide we are going to see this transmission model. Okay. And noise or error is a main problem of the signal which disturbs the reliability of the communication system. And each error control coding technique involves the use of a channel encoder in the transmitter and decoding algorithm in the receiver. So that will see in the transmission model. So this is the transmission model. So here you can see the input is a discrete source. So the discrete source means here sending ones, zeros like that. And this discrete source is applied to the channel encoder. So the channel encoder here adding the redundancy. So this encoder duty is going to adding redundancy. This is my redundancy. I'm going to adding the redundancy means extra bits or also called as parity bits, what it may be. So some additional bits going to add to this discrete source, and this source and the total bit sequence is going to modulate and entered into the channel. So the modulator is which converts this discrete source into a suitable form to the channel, compatible to channel. Why? My channel is analog. So here my aim is to convert into a waveform model. So the side is waveform channel. So the modulator duty is to convert this bits into like this analog form or waveform model. So that's that is we are using in modulator maybe ASK, PSK, FSK, QPSK or DPSK like that. Different types of modulator techniques are used to convert this banner sequence into a waveform model. Now this is compatible to the channel and the signal going to travel in this channel. Okay, so in the channel the noise will goes to adds up. So the noise is going to add. So due to this noise the errors is going to generate. So here you can see detector. So that is at the receiver. Here this 3 blocks which come to the transmitter and these 3 blocks which come into the receiver. Okay. So the receiver, the first part is a detector. So where the last part is modulator, here it is going to demodulate and detect the signal. Okay. And then after channel decoder is going to apply. So that means decoding algorithm is going to apply. Why? At the channel encoder, I am going to add the redundancy bits. It's not essential, but they are helpful to find the reduction. So here I am going to remove those additional bits. Why? The user not required those bits. The user required what that transmitter one, that is required for the user only. So not required these essential bits. Okay. So that's why the additional bits will going to remove at the decoder, channel decoder. Okay, and finally the information bits is going to apply to the user. So this is the transmission model of this under control coding. Okay, now there are many different error correcting codes depending upon the mathematical principles applied to them. But historically, these codes have been classified into linear block codes and convolution codes. So we have only two types, but actual to the syllabus, by the syllabus, you are having only the block codes. There is no convolution codes. So that's why in this module, we are going to cover block codes and cyclic codes. But cyclic codes is a subclass of this block codes. So that's why in this syllabus, we are only having block codes and cyclic codes. Okay. So what is channel encoding? Channel coding. So transforming signals to improve communications performance by increasing the robustness against channel impairments, noise, interference, fading. So that's all we know. Why noise is always adds. That's why you can call it as additive noise. Its nature is Gaussian. So that's why additive white Gaussian noise. Simply you can call it as interference. Interference that means adding the another signals which having the same frequency levels. So then our nearby frequency level, some interference you will get. Or another electromagnetic interference also having when you use the wired network. Why the channel may be wired or wireless. So in the wired channel, electromagnetic interference also there. And another one is of fading. So again fading has different types. Multipath fading. So a slow fading, fast fading, like that. But in multipath means number of reflections after the receiver will going to receive. So that is multipath. Why the signal have different paths to receive at the receiver, to reach at the receiver. So the signal is going to fade. Fade means it loses its amplitude. So that is a fading. Okay. So these are the impairments of the channel. So these impairments will going to reduce to increase the communications by channel coding. Okay. Next, waveform coding. Transforming waveforms into better waveforms. While modulating is used. So this modulator which converts this bit sequence into waveform. So again transforming into better waveforms. That means which is robustness to the noise. Okay. And structure sequence. Transforming data sequence into better sequences having structured redundancy. So these are the different characteristics of this channel coding. And what are the different types of channel coding schemes? So in the channel coding schemes are listed below. One is IARE, automatic repeat request, block coding, convolution coding, concatenated coding, and orthogonal coding. So these are the frequently used codings, but the syllabus only having this block code. Okay, but we go know what are they. So first one is automatic repeat request, IARE. So the receiver sends feedback to the transmitter saying that if any error detected in the received packet or not. There is a not acknowledgement and acknowledgement respectively. That means you're having any detected, not acknowledgement or acknowledgement. Just like a post. When you receive, you give some acknowledgement. I received like that. Okay. The transmitter retransmits the previously sent packet if it receives NACK, not acknowledgement. I'm not received. So again, the transmitter is retransmits. Okay, that is the automatic repeat request, IARE. Another is a forward error correction, simplex connection, error correction codes. the receiver tries to correct some errors. So there is a forward error correction. Another is a hybrid ARQ. Automatic request, So this is a hybrid. That means it is going to combination of ARQ plus FEC. So full duplex, error detection and correction codes. Whereas the FEC is simplex. Now it is full duplex, 2way. So this is a hybrid ARQ. And now we went into the black codes. So in the linear black codes, the parity bits and message bits have a linear combination, which means that the resultant code word is a linear combination of any two code words. So there is a black code. So here they are having the parity bits. Parity bits is nothing but redundancy or extra bits, and the message bits. So these parity bits and message bits having a linear combination. There is a linear black codes. So let us consider some blocks of data which contains k bits in each block. These bits mapped with the blocks which has n bits in each block, where n is greater than k. So here in the block code we can represent as n comma k. So n is the number of codes, number of bits in a code, or simply can call as code length, and k is the message bit. So number of message bits that can represent as k. So generally here we are going to use 7, 4. 7, 4 means the number of bits in a code is 7. Number of message bits is 4. So here the block codes can be represented as 7, 4. Whereas in problems we can easily understand the structure of this block codes. Okay, in the coming slides we are going to discuss about these problems according to this block codes and cyclic codes also. Okay. So the transmitter adds redundant bits, which are bits, that is n minus k bits. Here we're having n comma k. That is the block code size. So in n comma k, n is a code, a number of bits in that code, and k is message bits. So here I'm going to add n minus k parity. For example, we are taking as 7, 4. In the 7, 4, how many parity bits? We are having 3. Why? N is 7, k is 4. N minus k means 3. So that means I am going to add 3 parity bits for the 4 message bits. So here, for example, 1, 0, 1. So this is my parity, and 1, 1, 1. 4 ones. So how many bits here? 7. So in that 4 message bits and 3 parity bits. Okay, where the ratio of k by n is the code rate, it is denoted by r. Okay, so the n minus k bits added here are parity bits. So parity bits help in error detection and error correction, and also locating the data. So these parity bits having errors. So we have any errors, we can find by checking these parity bits. Then we can detect and correct that errors. Okay. So these parity bits are used for error detection and error correction. So in the data being transmitted, the leftmost bits of the code word correspond to the message bits, and the rightmost bits of the code word represents the parity bits. So it may be changed also, no problem. Why? It depends on the generator matrix. So in coming slide we are going to deal with the generator matrix. The generator matrix having the coefficient matrix. Okay, coefficient and identity matrix, that is called as generator matrix. So depending on the position of the coefficient matrix, the message bits are shifting or changing. Okay. So any linear block code can be a systematic code until it is altered. Hence, an unaltered block code is called a systematic code. Okay. Following is the representation of the structure of a code word according to their allocation. So here you can see n minus k parity bits, k message bits. Okay. So encryption of the data should not change the data. Why? Here the messages don't change. Why? So these message bits, k bits, are very, very important. My aim is to transfer this message bits to the receiver and to minimize the errors. So here we are going to adding these parity bits. So after adding these parity bits, there is no alteration or no changes in this message bits. Okay. So here you can see the information bit stream is chopped into blocks of k bits. Each block is encoded to a larger block of n bits. So it is nothing but code. So the coded bits are modulated and sent over the channel. Already we can see the transmission model. Okay. So the reverse procedure is done at the receiver. Same usual by his decoding algorithm. Okay. So here, what is the duty of channel encoder? It accepts k message bits and produces n bits. That is, n bits is the code word. So here I am going to add this n minus k redundant bits. N minus k redundant bits. So this redundant bits is nothing but extra bits. So here I am going to add n minus k extra bits to the k bits and finally produce n bit of code word. So the code word size is n and code rate also is equal to k by n. Okay. So here you can deal with the Hamming weight. So the Hamming weight of the vector u denoted by w of u is the number of non-zero elements in u. For example, here I am generated a code that is 11011001 like this. So here what is the Hamming weight? The number of non-zero. So here how many non-zero? 1, 2, 3, 4, 5. So this is the weight, Hamming weight of that vector. So that is denoted by w of u, the number of non-zero elements. And what is the Hamming distance? The Hamming distance between two vectors u and v is the number of elements in which they. So here we are using this module to sum or XOR operation between these two. Then you can find the Hamming distance between two vectors. So here it is known as d of u comma v. So what is d? D is the Hamming distance, and having two vectors u and v. By finding that module to sum or XOR operation between these two vectors, you can get the Hamming distance. Okay. So the minimum distance of block code, minimum distance, that is a day minimum, which is equal to minimum of I not equal to z, d of u I comma u z. D is the distance. So the minimum distance is the minimum weight of u. And error detection capability. So how many bits can be detected? Why? Because we are already saying why is error control coding? This is used for the error detection and error correction. So what is the capability of that code? So how many bits can be detected? How many bits of errors can be corrected or can be detected? There is d minimum minus 1. So first you can find the d minimum minus 1, then you get error detection, how many bits you can detect. But generally, according to our syllabus, you can detect only 1 bit. So you can detect 2 bits, but you can correct only 1 bit. So here you can detect 2 bits, but correction will be possible only for 1 bit. But according to syllabus, you can detect 1 bit and correct easily 1 bit. That is, you can correct. Okay. So error correction capability of a code is defined as the maximum number of guaranteed correctable errors per code word. That is nothing but small t is equal to day minimum minus 1 by 2. Day minimum minus 1 by 2. So that is error detection capability. Error correction capability. So this is a formula how to find error detection and how to find error correction. So first you must get the minimum distance. Then you can find detection and correction. Okay. So here you can see the maximum, matrix description of a linear block code. So in a linear block code, the block length C of the linear block code is equal to M into Z. So general formula, this is C is the code and code length. That is equal to M into Z. Simple matrix multiplication. So do you know the matrix multiplication? Then it is easy, very easy, and easily getting marks in this block code. Just you go to multiply this matrix for M. M is nothing but message bits. G is the generator matrix. Where G is the generator matrix. So Z is equal to IK augment P of K by N size. K by YK is the number of message bits. N is the number of codes. Generally, we are using 7, 4. So what here? 4 by 7. Here, my G size is 4 by 7. Okay. IK, the identity matrix. Identity matrix size is also 4. 4 by 4, I can use identity matrix. And P is the coefficient matrix. So, this is a way how to generate a linear block code. Easily, you can generate just by multiply the message bits with the generator matrix. Then you can get this code. Okay. So this is P is a coefficient matrix and I is identity matrix. So at the receiving end, the parity check matrix can be even as H. Y is not the end of generation. Again, you go to check at the receiver. Okay. So H is a parity check matrix. G is the generator matrix. H is a parity check matrix. By using parity check matrix, you can detect the error. Okay. So how can you generate this parity check matrix? Simply P transpose. P transpose means the transpose of the matrix P. What is matrix P? Is nothing but coefficient matrix. And I n minus k. So here n minus k, for example, n is 7, k equal to 4. Then what is the identity matrix size is 3 by 3. So here my I size, identity matrix size is 3 by 3. So when you go to solve the block code, you must require this coefficient matrix P. So in exam, they may give G, generator matrix, or at least coefficient matrix. This is a coefficient matrix. So y G equal to P augment of IK. So in this form, we can go to generate this G. Then we go to simply multiply y is equal to M into Z. So here having the message bits. For example, 1, 0, 1. For example, this is my message bits. So I am going to multiply this message bits by Z. Then I can generate the code. So it is very easy. Simply the matrix multiplication. So the G may having 4 by 7. Simply you get what you get? 1 by 7. So the code is simply 1 by 7 size. So that means like this one. This is just example I'm saying. So code is like 4 ones, 3 zeros. So the size is 1 by 7. Why? I am going to multiply here 1 by 4 with g size is 4 by 7. So when you go to multiply two matrices of two different sizes, then we get this size is 1 by 7. This is a row by column, and this is by row by column. So we get the first matrix row and the last matrix column. So that is 1 by 7 we got. Okay. So here this is C equal to MC. What is C? Code. M is the message. G is the generator matrix. So this is encoding in N comma K block code. So here you can see this is N minus K. What is N minus K? Redundant matrix. K is the message. So this is a redundant or parity bits. So here you go to add the parity bits at the channel encoder, and this parity will going to remove. Okay. So P is IK form. PIK. So P is the coefficient matrix, or simply you can call as P matrix, and I is the identity matrix with the K size. Okay. And for any K by N matrix Z with K linearly independent rows, there exists an N minus K by N matrix H. That is nothing but parity check matrix. So when you go to multiply this general matrix with the parity check matrix, simply get the null 0. 0. When you go to multiply the generated matrix with transpose of parity check matrix, then you got 0. And H is a parity check matrix. It is the form of IKP transpose. So previously you can see G equal to PIK form, where H matrix, that is parity check matrix, is in the form of IKP transpose. Why? When you given the parity check matrix or coefficient matrix, by using this coefficient matrix, you can generate Z and you can generate H also, simply. So here, this coefficient matrix is very, very important for generation of any these two. Why? You know the arrangement, that is equal to PIK form, where H is equal to IKP transpose. Simply you can transfer this one. Okay. But maximally in given exam, the G is directly, but not given also, you can arrange this G and H. Okay. Now what is a Hamming codes? So Hamming codes are a subclass of linear block codes and belong to the category of perfect codes. Hamming codes are expressed as a function of a single integer. So code length is here n equal to the power of m minus 1, and number of information bits k equal to 2 power m minus 1, and number of parity bits n minus k, that is simple as block codes. Error correction capability is only 1. So maximum here the Hamming codes are equal to the block codes. Why? Here also n minus k parity bits and error correction capability is also 1. Okay. So for example, here you can say 3 parity bits are there. For example, n minus k. So what do you get? 2 power m is 8 minus 1. What is my size? 7. Simple. Okay. Now this is one example. Here you can say 7 comma 4. So 7 comma 4 is simply the block code size we can take in. So H is IKP transpose, where G is P IK transpose. So here we can see H equal to I P transpose, where G equal to P I K. IK is K is the size. So this is my identity matrix. This is my identity matrix of size 4 by 4. And this is my coefficient matrix P. So here what I am saying, H equal to IP transpose. So you can see. So the first row is 0, 1, 1. So A transferred as column. And second row is 1, 0, 1. This is transferred as column. And third one is similarly 110. So this is making as column. And the last row, fourth row, is as fourth column. So this is a P transpose. So in this problem or in this block code problems, parity or generator required this coefficient matrix. Required coefficient matrix. Without coefficient matrix, we can't generate this G and H. Without G and H, we can't do anything. Why? For code, I require C equal to M into C. For syndrome calculation, C equal to R into H power T. What is H? H is a parity check matrix. By using syndrome, here I am going to detect at what place the error will rise. Okay? So, this content of information is taken from Communication by Saman Hacking, third edition. And again, the digital communication by Saman Hacking also. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.